This brings us to the end of the opening session, and we will continue immediately with the first keynote of this conference. So it is indeed my great pleasure and honor to introduce the first keynote speaker, which is Dr. Sumit Gulwani. He is a computer scientist seeking connections between ideas, research, and practice, and with people with varied roles. So he is also the inventor of many intent understanding technologies, including the popular flash fill feature in Excel, which we are quite familiar with, perhaps. He's the founder of the PROS research and engineering team at Microsoft that develops APIs for program synthesis. And his research, one of the very powerful aspects of his profile is that his research has found its way into many products, including Office, Visual Studio, SQL, Power Query, and PowerShell, many products that we use on a daily basis. So Sumit has authored many award-winning papers, 10 award-winning papers, and delivered many keynotes and invited talks, and also the recipient of a number of prestigious awards, including the ACM SIGPlan Robin Milner Young Researcher Award for pioneering contributions in program synthesis and intelligent tutoring systems. So it is indeed my great pleasure to now invite Sumit on stage to deliver his keynote, which will be entitled AI-Assisted Programming, Applications, User Experiences, and Neuro-symbolic Techniques. Sumit, please.
Hello, everyone. Okay, thanks, Abik, for the introduction. And it's a great pleasure and honor to be here. I'll start by giving a tribute to my father, who unfortunately passed away last month, unexpectedly and rather untimely. He had an incredible influence on my research work, most of which I'm going to talk about today. So last year, Microsoft arranged for a photo shoot for me to recognize some of my work. And just a few days before my dad passed away, I was very lucky to take some of his pictures in the same spots. He retired as a civil engineer, and he always aspired to become a better computer user and would always ask me different kinds of questions. He was also very interested in learning more about my research work. And this curiosity of his inspired me to pick problems and solutions that my father could relate to. I'll share with you one such a story. So several years ago, I was returning home from a conference, and there was a lady sitting next to me in the airplane. So she was very impressed to know that I work for Microsoft Research and that I have a PhD in computer science. So I ought to help her with the task that she was struggling with. She opens up her laptop, fires up Excel, and shows me a column of names and asks me, how can she reformat these names? Now, at that time, I had no idea about the programming model underneath Excel. So I had to excuse myself out of the situation. But after returning home, I searched for a solution to this problem on Excel help forums. And this is when I realized that there were many people who struggled with such simple repetitive tasks. In fact, 99% of people who use computers, like my dad, don't know programming, and they struggle with such tasks. Oftentimes, they communicate their intent to an expert on a help forum through input-output examples. And then the expert would send them formulas to try. So this is what inspired me to develop this feature called Flash Fill, which allows automation of such tasks from just one example in many cases. So this feature will look at this input-output example that the user has provided and will generalize this into a program and run this program to automate the task for the user. Now, there are cases where the computer may not be able to read your mind from just one example, as this scenario illustrates. Here I have a bunch of medical billing codes, some of which have a right bracket at the end, while some don't. Suppose my goal is to clean this data by adding a right bracket wherever it is missing. So if I give one example, the tool comes up with the simplest generalization, which is to add a right bracket everywhere. Maybe this is what you want, and then you'll be done. Otherwise, you'll observe that rows 6 to 10 are incorrect. And you can fix any one of these, say row 8. And once you do that, Flashfill is able to generalize to the right intent that you have in mind. So Flashfill can automate a wide variety of tasks. In this case, I want to generate an abbreviation. And from just one example, it will complete the task for you. I can do things in reverse order. I may not have spaces. I may put periods, and it will all mostly work. So let's see now how does Flashfill actually do this. So Flashfill actually restricts the search for programs to an underlying domain-specific language. So in this case, this language consists of a standard string algebra that allows you to compute substrings of the input string and concatenate them together, possibly with constant strings in the middle. And the positions for the substrings can be computed based upon regular expressions. And then there is also an if-then-else construct at the top to allow for processing strings in different kinds of formats. And now, given some input-output examples from the user, our goal is to search for a program in this restricted domain-specific language. Now, one simple idea might be to enumerate all possible programs one by one, say in order of increasing size. But this simple idea is not going to work because this language itself is infinite. So what we do is we use a top-down goal-directed search strategy where we push the examples down the structure of the grammar. And this is what we call symbolic backpropagation. So if there's one technical idea you take away from this talk, let it be this, as it describes how Flashfill actually works, and others, and so do other programming by example technologies. So suppose my goal is to convert the input on the left side of the arrow to the output on the right side of the arrow. And suppose I want to synthesize an expression of the kind concatenate of E1, E2, where E1 and E2 are recursively defined in the grammar. Now, my goal is to push this input-output example spec for the concatenate expression to input-output example specifications for the parameters of concatenate. Because if I can do this for every operator, then I can just recursively solve this problem. So essentially what I'm asking is, what should E1, E2 be such that the output of concatenate E1, E2 produces Roy dash a big? And this question is answered by leveraging the inverse of the concatenate function, which in this case corresponds to 8 different choices, which represent the different splitting of the output into 2 different parts. The green choice will lead to the correct answer, and the other choices will be killed in the search exploration process. Now, this green choice leads to 2 different sub-goals. One of them says that E2 should evaluate to a big. And let's say one of the choices for E2 is a substring expression in the grammar. And now when we do symbolic backpropagation, we are really asking, what should P1 and P2 be so that when I compute the substring on this input, I get abhik as the output. And this is answered by figuring out all possible occurrences of abhik inside the input string. And there are 2 such occurrences, of which the first green one is going to lead to the right answer. So you might want to compare symbolic backpropagation with the what is called neural backpropagation in machine learning. And there's an interesting relation between the two. So this symbolic backpropagation, which I showed you, is really searching for programs in an underlying domain-specific language. Whereas neural backpropagation in machine learning searches for weights over a neural network. And then the symbolic backpropagation that I showed you is done just once on a single task at inference time. And it ends up finding a program that matches the specification exactly. And in contrast, numerical backpropagation is done many times across a wide variety of tasks that have been provided at learning time. And what it results in is a best effort loss minimization. So what this symbolic backpropagation really does over the underlying domain-specific grammar is to produce multiple sub-goals at each stage. Now we can actually try out these different sub-goals in the order of their likelihood to succeed so that we can quickly figure out the green sub-goal. And this can be done with various heuristics, which you can author manually, or you can actually even learn them using machine learning. And then what we figured out is that sometimes it gives you a 10x speed up in the underlying search process. And at the end of this process, you are left with many different programs, each of which is consistent with the examples that the user has provided. So now you need to rank these programs in order to figure out the intended program, because most of these programs will be an overgeneralization of the input-output example that the user has provided. So you can rank these programs based on the features of the program. You can pick a program that is small, that uses a fewer number of constants. And interestingly, you can also rank these programs based on their semantic behavior on the rest of the inputs that are available over which you want to run this program. For instance, a program that produces output that is more uniform is more likely to be correct. So Flashwheel is able to automate a wide variety of tasks. But there are many tasks that it cannot do. And the user experience for programming by examples is so inviting that it does not prevent people from trying it on tasks that it was never meant for. So I designed Flashwheel for automating syntactic string transformations. And it is not able to do string and number and date transformations because it does not have support for those in the underlying domain-specific language. And then when it fails, people talk about it. And there was this tweet that went viral in October 2018, where someone wrote, "Oh, look, AI is going to take over the world, but this is what Excel auto-populated for me today." Someone had given an example mapping DEC to December, and then Excel auto completes OCT to October and JNM to January. In fact, some people even came to my rescue by saying, this is how we should have named months in the first place. But the best part about this user feedback is that it really points you to important directions that users care about. And this is exactly what we did. And now the new Flashwheel++ capability that should hopefully be released soon can automate many such date-time tasks, date-time transformation tasks. So here, what I have is a raw data set of emergency calls. And suppose my goal is to extract the red date and map it to the corresponding weekday, and the green time and bucketize it into a 3-hour bucket. Now just imagine how much time it will take a data scientist to actually do this. They will have to write a lot of code, and it will take several minutes for them to probably write a program to actually do this. But Flashwheel++ can automate this from just one example. And not only that, it actually generates readable code for such transformations. And it can generate this kind of code in many different languages. And here I'm showing it in Python. In fact, this has been one of the biggest asks from Flashwheel users to be able to look at code for transparency and so that they can also incorporate it as part of their bigger workflows. In fact, this code also has a lot of educational value. So the first 2 lines tell you how to compute the right substrings. The next 2 lines teach you how to cast those substrings into datetime objects. In fact, I did not know before that %A is the magic sequence of characters that you have to use to convert a datetime object into the corresponding weekday. So this capability is already out as part of one product called Power Apps. And then this will soon be released as part of many other products, and hopefully also including Excel. Now, let me talk about the challenge in handling or in designing FlashFill++. So to do FlashFill++, we had to extend the underlying domain-specific language with number and datetime operators. And it's also many operators that represent stylized ways of doing things in many different target programming languages. And this leads to a 10x increase in the size of the underlying domain-specific language for FlashFill, and scalability becomes a challenge. And if you recall, the heart of FlashFill was a symbolic backpropagation, which essentially works when the number of inverses at each stage are very small. But in this FlashFill DSL, FlashFill++ DSL, we have operators that have infinite number of inverses or very large number of inverses. And I'll show you one such example here. So suppose my goal is to take this input string and extract the first name and lowercase it. And this can be done using the toLower operator. Now, if I ask what should S be so that toLower of S produces ABHIC, well, there are an exponential number of possibilities because each character in ABHIC can be independently uppercase or lowercase. However, I'm not using the information that the subgrammar for S will only allow me to compute substrings of the input string. And if I take that information into account, then I realize that there are only 2 variants of ABHIC in the input string. And that can be used to significantly filter the results of symbolic backpropagation. In fact, here is another such example. Suppose my goal is to extract the price from the input string and then round it up to the dollar amount. This can be done using the round num expression. But the inverse of round num on 25 will really give me infinite possibilities, because any number between 24 to 25 can be rounded up to 25, for instance. But if I use the information that the num expression in the grammar can only refer to numbers that exist inside the input string, then I realize that there are only 2 such numbers that exist in the input string, and there are pretty much 3 choices, so that the output of round num is 25. So I can either extract 24.58 and round it up or round it nearest to 25, or 25.6 can be rounded down to 25. So this idea of combining some information from bottom-up synthesis and using it to filter the results of top-down synthesis is what really enables FlashFill++ to maintain its scalability and efficiency. Now, there are some tasks which cannot be done using standard programming. For instance, mapping a city to the respective airport code, or mapping a numeral to the corresponding word representation in some language. For this, you need access to some knowledge bases. In this scenario on top right, the user wants to extract the color of from the iPhone description. And this possibly cannot be programmed using regular expressions because the data is rather quite noisy, but it requires entity recognition capabilities. And at the bottom right is a very interesting use case of potential use case of FlashFill to generate practice problems for language learning. But FlashFill cannot do this because this one requires access to some parts of speech or natural language understanding. So our key idea to accomplish all these kinds of tasks is to combine the power of Flashfill with GPT-3. So GPT-3 is this large language model that was released by OpenAI last year, and it has an amazing set of capabilities as it also supports few shot learning. For instance, if you give this prompt to GPT-3, where I'm trying to map a country to its capital city, it is able to actually produce you the right output. But one may ask if Flashfill tasks can also be handled using GPT-3, and the answer is, not really. So here is one simple task where I want to extract the first 4 characters, and even after giving 4 examples, GPT-3 does not produce the right output. But we can combine the complementary powers of Flashfill and GPT-3 to be able to handle the kinds of tasks that I showed you on the previous slide. And we do this by extending the Flashfill DSL with some operators whose execution semantics is provided by GPT-3. So for instance, instead of simply computing substrings of the input string, I can also have some features of the input string, which pretty much represents the ability of GPT-3 to be able to do some question answering. Or instead of computing positions in an input string based upon regular expressions, I can compute positions based upon parts of speech or different entities that occur in the input string. And this really leverages the natural language understanding capability of GPT-3. And by combining these complementary powers of Flashfill and GPT-3, we are able to handle many semantic transformations as well of the kind that I showed you earlier. So my sister, who parents a 6th grader, recently figured out that Flashfill actually appears in computing textbooks, middle school computing textbooks in India. And my dad was so proud then. But there's a much bigger opportunity here. So here you see Flashfill being used as a task completion utility. But with Flashfill++, we can actually generate readable code. And this can facilitate computational learning in classrooms. Students can now see the logic and the exact syntactic details of how to accomplish these simple tasks using different programming languages. So my dad shared every research paper I wrote, but it is after the Flashfill paper that he told me that he understands my research for the first time. And this is what inspired me then to push this field much further. So it turns out that not only string transformations, but there are a wide variety of other tasks where examples are a very natural way for the user to specify intent. And here's one such scenario, taken from a data science assignment in a data science course. So the instructor provides the students with a raw semi-structured text file and challenges them to write a script to extract structured data out of this file so that then they can do some further processing. The instructor even provides the students an initial script to build on top of. Let me show you how this experience can be if we were to use programming by examples paradigm instead. So here I have loaded the same file in our playground. Suppose I want to extract the championship names. So I give one example and then another. And then after 2 examples, the system is able to generalize it into the right parsing capability to extract all of the championship names. If I want to extract the year, now just one example suffices because my interaction is already putting some structure on the document. Now let's say I want to extract the score. And after I give one example, then the system gets it wrong in the 3rd record because it is in a slightly different format. But what if this 3rd record was not in your viewport? It was in the middle of a large file. And then, even as a programmer, all bets are off because you might end up writing a program and not even know that you have made a mistake, because you might not possibly know all the different kinds of formats that exist in the document. But in case of programming by examples, there's a very interesting possibility. So what we can do is we can take the multiple top ranked programs that have been synthesized from one or more examples and run them all on this document. If they all give the same results, then it doesn't really matter which program you pick. But if they give different results, which is what happens in this case, then you know that this is a place where the user needs to pay some attention. And if you do that on this scenario, the system prompts the user with two different outputs and asks which one you want. And the user probably says, in this case, I want neither, but ends up giving the correct example. And then the system is able to generalize it to the right intent that the user has. So this interaction that I showed you can be applied to pretty much any kind of semi-structured document, including semi-structured spreadsheets, web pages, PDF documents, even JSON. And many of these technologies have actually been released as part of the capability called data connectors in Power Query, which is a business analytics offering from Microsoft. In fact, recently, these capabilities were used heavily to build dashboards from various COVID-19 datasets. So when we initially approached the Power Query product team to consider putting these technologies in their product, they initially told me that we don't have time to build a great user experience, like what I demonstrated you earlier. Can you make this work with 0 examples? I thought making it work with 1 or 2 examples was already quite a big deal, and have they gone crazy? But then when I thought more about it, it made sense. So for instance, if you have this custom text file and you want to extract a table out of it, then giving 1 to 2 examples of the many tens of fields might actually be very tedious. So if you can do it completely automatically, it would be a much better user experience. Or if you have a web page and you want to extract this table, you don't really need to provide examples. As a human, you are already able to figure out what the various fields are. And if humans can do that, we asked, can AI do that as well? And this is what took us to developing this capability called predictive synthesis, which can also work from 0 examples. So you can liken this to learning from a 0-shot learning as opposed to a few-shot learning. And here we cannot use symbolic backpropagation because we don't really have a goal to begin with. But what we do is we do a bottom-up enumerative search. But instead of searching for programs, we actually search for structures, likely structures, over a small prefix of the document. And then we end up picking a structure which looks very uniform and has maximal coverage of the document. And then once we guess what the examples are going to be, then we use our standard programming by example technologies to then learn programs. So now let me move on to another part of the talk. There are several tasks that can be specified using examples very naturally, but there are some tasks for which natural language is actually better. For instance, suppose I want to take 2 pictures and combine them horizontally after adjusting their height, and then save them to the folder college reunion. That was the last task that I helped my father with, who wanted to experiment with different pictures for his golden anniversary reunion that was coming up in December. I recently came across one of his handwritten notes where he had written down many such "how do I do X" kinds of questions. And the ones that I had answered for him, he had even written down those answers. But some questions were left unanswered. But sometimes I pretended to be too busy. That's why AI agents are the best. They're always available. And we actually ended up, a few years ago, solved exactly the same problem. And the idea here was very similar to that of a programming by example technology, where we use several heuristics to infer or synthesize many programs in an underlying domain-specific language, and then use ranking techniques to pick between different programs. But the challenge with any such NL2 code technologies that we developed was that they would not be very effective when there would be variability in the natural language description. And furthermore, they required a lot of domain-specific heuristics. So recently, there has been a very big advance in this area of natural language to code. And it is a system called Copilot that has been developed by GitHub. So it is able to provide you suggestions for whole functions and in many different programming languages. In fact, people who use it want to continue to use it, even though it is only providing them correct code 35% of the time, because it is really able to produce very surprising outputs. And if you have not yet tried it, I would highly recommend that you try this out. So Copilot is based on another large language model from OpenAI called Codex, which is similar to GPT-3, but it has been trained on code. And in fact, this large language models for code has been one of the most happening things in the area of machine learning for code recently. So many large organizations are training models of their own. There is AlphaCode from Google, Encoder from Meta, P5 from Salesforce. And all these models have been trained on a lot of natural language corpus, as well as a lot of code corpus that is publicly available on GitHub, Stack Overflow, and so on. But one challenge with these large language models is that they are not very precise for a given task domain. And this creates opportunities for you all to develop interesting workflows on top of these large language models to make them work effectively for a given domain. And let me share with you some such ideas. So one idea that some colleagues have been trying is to fine-tune these models with some more deeper program properties, such as based upon static analysis or dynamic analysis. One idea that we tried out recently was to be able to guide the output of the large language model in such a way that it meets the underlying target domain constraints. So for instance, if the large language model generates this partial SQL query from natural language, and it is about to emit the next token, we can tell it that, oh, don't produce 2, because if you produce the digit 2 here, then this query cannot possibly be completed into a valid SQL query. And this will prompt our system to, or Codex to, output some other tokens which can actually be completed into a valid SQL query. Yet another idea has been to leverage multimodality. So examples in addition to natural language specification. The AlphaCode system from DeepMind generates lots of programs from natural language description and then picks between them based upon the test cases that have been provided in order to be able to solve competitive programming problems. And some of my colleagues at MSRI have developed a system called Jigsaw, which takes the output from large language model and then applies different kinds of repairs to be able to generate lots of candidates and then picks from those candidates based upon the tests or input-output examples that have been provided. Let me share with you one interesting idea that we experimented with in the context of combining PBE, programming by example technologies, with a large language model. And this was to synthesize regular expressions. So here is a potential natural language specification and an example-based specification for synthesizing a regular expression. Now, neither of these descriptions are precise, but maybe together they are. Right? And this is the power of multimodality, of combining natural language with examples. Either of them is ambiguous, but maybe the ambiguity cancels out. So when we try out just using GPT-3 or Codex on the natural language specification, we observe that we do not get any correct result. But we notice that the different candidates that GPT-3 returns contains very prominently the components of the target regular expression. And then on the other hand, if we were to use just programming by example technology on on example part of the specification, then we notice that it overfits or doesn't really scale if you provide a large number of examples. But then we can combine these two complementary capabilities, and our idea is to use PBE to search on the components that occur prominently in the results that have been written by GPT-3. So we use GPT-3 to obtain a set of partial expressions or components, and then we perform we perform search for programs or regular expressions, in this case from example-based spec, on these components. Now, what can be other forms of expressing intent? So one way where AI can assist you in your programming tasks is by just watching what you have been doing in the recent past and then making suggestions. For instance, suppose I am authoring a new class and maybe I wrote this. If I let Copilot take over, it will give me exactly what I intended. Very impressive. But let's say I'm editing this part of the code. Now, can you guess my intent? Likely not. But what if you saw what I was doing just a little while ago in a slightly different part of the code base? I had this expression for converting Fahrenheit to centigrade, and I replaced this by a method call. Then I made another such change. And now you can probably guess what I'm trying to do here, which is to replace this expression by the same method call. And this is what we call repeated edits, and can actually be automated through this example-based interaction. After seeing few examples, I can actually then produce you the intended transformation in some other parts of the code base. And this works very similar to how Flashful works, except that the underlying domain-specific language is not of string transformations, but it is of code fragment transformations. So this is the initial user experience that we built for this capability, where there were 4 boxes, and the user has to provide all the different code fragments that they want to transform in the top left box. Then they provide an input-output example on one of those code fragments. And then when they press the magic button, the system converts the rest of the inputs into the intended outputs. But there's a big problem with this user experience. It requires a lot of switching between different windows and copy paste. And this is not going to be good for maintaining the flow of the developer, because they might often start doing the task, and then when they realize that they could have potentially automated it, they might not want to get back into a starting mode, but might want to just continue and finish the task. So to deal with this challenge, we developed another idea, which is another t-shirt that I sometimes sport for my keynotes. Every class you break, every line you paste, every move you make, I'll be watching you. And this is what the technology does, watches each keystroke the developer is pressing. And then in this noisy trace of keystrokes, it tries to make some sense. It tries to figure out some edits which are repeated, and they become the examples for us to then use the Flashful for Code technology to be able to generate the intended rule for doing those transformations. So the developer does not provide examples explicitly, but these examples are implicitly present in the noisy trace of keystrokes that the user is editing. Now, this can lead to another challenge, because now this looks just like Clippy. We don't want to become Clippy for code. For instance, if the user makes 2 changes of an integer to string, we don't want to raise our hand and ask the user, oh, do you want to rename all integers to strings in your code base? In fact, once a user deleted some parts of the code base, and the suggestion that came up was to delete the entire code base. And this is where we need to use some extra signals to maintain the right precision recall trade-off. For instance, we make use of cursor location. We leverage any diagnostics that are present. We also run the potential intended edit script on the rest of the code to see what its effect would be. And then we achieve the right precision recall ratio that is needed for these repeated edits. So in terms of predicting what the user wants to do next by watching what they've been doing in the recent past, we can cover another class of transformations also that I call related edits. For instance, at the top, what you see is the user is removing a parameter from a method, and then they will be removing all the respective arguments from the respective method calls. And they might have to do this at multiple places in the code. So this is not a repeated edit as much as it is a related edit, because these tasks go hand in hand. So once the user starts doing this task in any order, we have a potential to suggest the rest of the task to the user. And this is what we call related edits. But here the patterns are not learned from the current user, but these patterns are learned offline from traces that we have collected from many other developers in the past. So these are the 4 ideas that I mentioned to you, which define this feature called IntelliCode suggestions that ships in Visual Studio. And it has been quite popular. So today there are around 4 million accepted suggestions per month, with several hundreds of thousands of users, monthly active users for this technology. And we often see very happy sentiments from some of these users who either discover this technology or are surprised by the suggestions that it sometimes produces for them. So what I described to you here is just a point solution in the broader space of AI for software engineering. You can imagine helping the user while code authoring or code editing or refactoring. You might be helping them with either boilerplate automation or bug fixing. And these kinds of technologies can be also surfaced either in the editor or even when you're trying to do builds. And then there's a big solution space as well. So the repeated edits technology that I talked to you about, which is part of IntelliCode suggestions, ends up doing some boilerplate automation using DSL-based synthesis, and the learning happens online from few examples as the user is making edits in their code base. And then the related edits technology that I showed you does an offline learning from lots of traces that we have collected of developer workflows in the past. In fact, another technology called API Fix, which is some joint work with Abhik that I did not get to talk about, helps you with code migration across different libraries. And Copilot helps you with all these different tasks, but it uses transformer models instead of DSL-based synthesis. So you can pretty much pick any combination here, and it will give you an interesting problem to solve. One aspect that we are very excited about is to combine DSL-based synthesis with that of transformer models. And then moving on to the last part of my talk. So let me motivate it by sharing another observation from an Excel help forum. So the Excel user wrote this formula that has an error, and the compiler gives this error message. So how many of you know what the fix here is? Right. So like me, many of you do not know what the fix is because the syntax is actually quite cryptic. And some of you who know, are like the Excel help forum experts who are able to make sense of this formula without any further need for a specification from the user. And this is the opportunity for automation here. So normally when we chat with each other in natural language, we can make grammatical errors. I may even miss some context, but still you can understand the other person. But when you're working with a computer, a single character mistake, computer refuses to understand you. Then here is a case where the user is missing a parenthesis after this point, but the compiler is suggesting putting a parenthesis at the very end. Because compilers make the assumption that whatever they have seen up until now, before failure really occurs, everything is actually correct. And this is the challenge with compilers. They were never built for nicely handling bad cases. They're always designed to handle the correct cases. And even if the compiler knows what the error is, they do not make any attempt to fix, because there's no unique fix. But what we know is that if we bring some naturalness into context, then we can actually recommend the right fixes to the user. And does someone know what the error here is? So instead of length, it should be length. So we designed a technology to be able to fix these kinds of errors. And let me quickly show you what the architecture looks like. So we have a buggy formula from the user, and then how do you get to a repaired formula? So what we do is we use a module to enumerate many different repair candidates. And in order to do effective enumeration of repair candidates, we use a neural module to predict where the errors might be in the first place. And then once we get multiple repair candidates, we rank them using a neural module in order to then serve the right formula to the user. So this architecture works extremely effectively, much better than the best symbolic and neural technique that we tried it on. So Codex apparently has an API called Codex Edit, which is used for editing formulas, but our neuro-symbolic architecture works much better. We recently released this for PowerFX formulas, and hopefully this will also go out for Excel in the near future. And there are very fascinating directions to continue this work forward. And one of them is to combine or leverage large language models and combine them with symbolic techniques to be able to handle more sophisticated kinds of repair. But before I conclude, I want to focus on talk about one very interesting application of repair. And this is in the context of a sector that AI has not disrupted yet, education. What you see here is not a stock picture, but taken by a colleague at Cornell in the office hours of their intro programming course. And the line actually extends around the corner. And what is the student at the end of the line thinking? Will I get those few minutes with the TA or not? And the challenge with CS education today is the demand for these classes is 5 times higher than the current availability. And another sad statistics is that amongst US minorities, there's an 80% dropout in these courses, likely because the technology stack here is not very adequate. So what is the first challenge that the students face with when they learn programming? Well, syntax errors. So here's some Python snippet that has a syntax error. And what is the message that the student sees? Expected colon at the place where count is. Now, not even knowing Python, I can tell you that this does not look correct to me, because I already have a colon here, and I can't possibly be having colon, just after else. So the last mile repair technology that I described a while ago can potentially be applied in such contexts to be able to fix these syntax errors for students. The next challenge that student faces after syntax errors is semantic errors, functional errors. Now, if a student code passes 4 test cases out of 10, are you just going to give them 40% marks and maybe point them to a sample solution? I don't think so that's sufficient. What the student needs to know is how their attempt, which reflects their thought process, can actually be lifted into a correct solution. And one of the techniques that we designed earlier on was to search for these kinds of repairs on an underlying domain-specific language of repairs for that particular programming assignment. But when the repairs got harder, we tried another interesting idea, which was to look for expressions in other students' correct submissions. And here's an idea that we are actually trying out in a classroom, where let's say a student makes an error and the teacher provides a fix, and then another student makes a similar error in the future. And then we can use this flash fill for code technology or the IntelliCode suggestions technology that I showed you for repeated edits to be able to serve the feedback to the student. But all these technologies are just research papers. And unlike most of the other work that I talked about before, they are not in production yet. And in order to make them real, much more robust, we need to do a lot more here. And this is what where I would like to state a grand challenge for designing an AI bot that can provide feedback to students, just like a human TA. And the success metric, is very clear here, that students should learn better and faster. And we have two interesting things to leverage. So first is the past learning journeys of students from around the world, year after year, who are trying out similar kinds of programming problems and at large are making similar kinds of mistakes. So if we can gather this data and we can potentially leverage the power of large language models that seem to have amazing capabilities now, and these models can actually be trained on this student data to make them more precise, and also be married with symbolic techniques in order to achieve a very high precision that would be needed in the classroom. Because you would not want to send your child to a class where the teacher is only 30% correct. The precision has to be in high 90s. So all in all, a fascinating area to drive advances in neuro-symbolic techniques, which was the implicit message behind my talk. So we have decades of advances in symbolic techniques. And the great thing about them is that they can guarantee correctness or relatively much more correctness than machine learning techniques, and they require much less data. On the other hand, the past few years have seen amazing advances in neural techniques, especially large language models recently. They're very broadly applicable and they handle different kind of fuzziness. And I believe that some of the next generational foundational AI advances are going to be built around creative ways to combine these neuro-symbolic techniques. And I showed you a few in my talk, so let me quickly just revise them before I conclude. So one of them was that the neural module is the main driver, and the symbolic module is actually providing some help. And we saw this in the work on constrained semantic decoding, where the symbolic module was able to guide the output of codecs token by token. Or it can be the other way around, where the symbolic module is the main driver and the neural module provides some assistance. And you saw this in the work on last mile error repair. And even the work that I showed you on Flashfill++ that was generating readable code, that actually also uses this architecture, because you can imagine renaming the temporary variables that Flashfill++ generates into much more meaningful variable names. And this can actually be done using codecs. Or the two modules can play both significant roles. And one such way to arrange them is in a pipeline architecture, which is what we saw in the regular expression synthesis, where the neural module was producing various sub-expressions over which the symbolic model then did the search. Or they can also operate in parallel. And one such instance that I talked about was that of semantic flash fill, where flash fill was able to handle part of the transformation and GPT-3 was able to handle the other part of the transformation. So I love to acknowledge my team for the breadth and the depth of the work that I presented today. And my team actually releases most of what we do for Microsoft products in the form of an SDK, which is made available for free academic use. And these are the 4 intent specification mechanisms that I talked about. And I believe that the future is really about taking programming closer to human conversation. And this is where we will need to leverage multimodality and interactivity. And as I mentioned, neuro-symbolic techniques shall drive some of the very foundational AI advances, and programming is a great area to power these. And the reason why this area is so very important is because I believe that it can empower everyone on the planet, like my dad, to accomplish more. Thank you.
Okay. Questions? There are 2 standing mics over here, so you can make your way to the mics. Okay.
Hello, my name is Ari van Deursen, Delft University of Technology. Thanks for a wonderful and also very personal talk. You talk about education in severe need for disruption. I agree. But GitHub Copilot is delivering this disruption, as in all textbooks on programming need to be rewritten because the students will just enter it in GitHub Copilot. Can you maybe shed your light on how GitHub Copilot can be used nicely in introductory programming?
Yeah, so that's a very good point that you bring up. So in my talk, and I'm not acting as a pedagogy expert, and this is something that needs to be thought about more carefully. But in terms of automation, what I'm suggesting is whatever is the role of a human TA or a teacher who feels constrained to provide personalized feedback to 30 students in a classroom, or sometimes thousands of students in a MOOC, is what the technology can potentially help automate. But what is it that we need to provide feedback on is something that the pedagogy experts will need to decide. For instance, if a student has a mistake, you don't want to actually even show them the repair. Sometimes you might just want to say, oh, you have only struggled for 2 minutes, keep trying more. But if a student has struggled for 2 hours, then you might even want to point the student, oh, remember the feedback I gave you 3 days ago? Maybe this is a similar problem, to that. So that is the role of using AI in classroom. But back to your question about what should the pedagogy be, it's a great question. And we cannot keep blind to the technological innovations that are going on. Copilot is real. It is already in the hands of students. So we will have to think hard about how this can be part of the instruction. So I'm not answering your question. I'm just reiterating the significance of your question. Maybe one cheap analog that I can draw is with calculators. So we still want to teach students basic addition, multiplication, but we also want to acknowledge the fact that when students move on to higher grades, they can take calculators for granted.
Other questions, please?
I'm Shane McIntosh from the University of Waterloo. Great talk. Yeah, I really enjoyed it. And I'm wondering, like, when the context is ambiguous, like there are multiple answers within the examples, how does the technology make a decision?
Yes. So very good question. And I feel that, this has pretty much been the turning point behind, the success of these technologies compared to the previous era a decade ago. A lot of work on synthesis was from doing, full functional specifications and formal logical specifications, because people don't really, write that, right? And so the magic is really how do you handle very little intent, which is very ambiguous as you observe. And the idea here is to build biases around what is more likely in the real world. So lots of these ranking techniques that we have, which are able to pick out the right answer or a right answer from lots of choices, which are all consistent with the ambiguous input. They have been trained on what is more likely to happen in the real world, right? And also we often also get inspired by how humans go about doing such kind of problem solving. So if I show you a given example, or if I say things in natural language, as a human, you are able to figure out what the right intent is, because you're able to build on your common sense reasoning or your past knowledge of the word and so on. And I think this is what the ranking techniques are also trying to emulate. So by marrying these ranking techniques with the traditional symbolic techniques that we have developed in our community, I think this magic arises after that.
Julia Luong, so I would first like to thank you for your tribute to your father. I thought it was very we can draw lots of inspiration from people who are somehow not experts and in our area, and really try to help them. I mean, we can really do the work that has the most impact if we can draw inspiration from people, such kind of non-expert people. So I had a question about when your father wanted to organize his photos. So that seems kind of the query that you posted seemed kind of very top down. So sometimes though you want to describe how the output is going to be used. Like maybe I have my photos, how do I'm still expressing this in a top-down sort of way, but how do I get it into a certain format without actually specifying kind of the complete story? I don't know if it's clear what I mean, but if you think about a function, it has input types and output types. And that function can be just, it's not working anymore. I think, I'm not, sorry. The function can be kind of the connection between the input and the output, and then the output, other things will happen downstream with those output types. So if you have a solution for like just that function in the middle.
Yes. So you're right, Julia, that there's a lot of ambiguity here. It's not even clear, what the inputs and outputs typically are. And again, the magic here is to do this kind of search over a very restricted domain. So that's why all the systems that we have built on NL2 code operate well, but in a very restricted domain. And here we search over the operators that the underlying scripting platform actually provide you. So the work that I did initially was over a language that Windows Phone actually had underneath. And what I helped my dad with was the scripting app on iPhone. But once you narrow down these kinds of operators, then you have a very restricted domain-specific language to search with. And of course, you are absolutely right that you also need to guess what the inputs might be, what the outputs might be. And this is exactly what these different ranking modules that we have are doing. The challenge really arises when you want to do this in a much broader domain or for a wider variety of tasks. And this is where I fully agree with you that these techniques do not work very well. And this is where large language models are now really changing the game and pointing us to very interesting possibilities. And that's what we need to now actually start building on, not the various kinds of heuristics or hacks that we designed earlier, which were leveraging the fact that this is how the domain is very restricted.
Thank you.
There's a question here. Hi, I'm Sridhar Chamarkona from IIT Tirupati, India. So interesting talk. I was wondering, like, there was this intelligent tutoring systems way back where they were trying to look at learner characteristics and so on, and try to help students in this. So I was wondering if there was some exploration done, or is there a connection that has been tried from the perspective of AI assisted programming from intelligent tutoring system? Because there was a lot of knowledge base that was built. I mean, at least I've not seen directly, but I when I was looking at the literature, I found that. So is there some work that tries to combine the AI kind of space with the ideas, and what are your thoughts on that direction?
Yes. So I think one of the biggest efforts in this space is being done at CMU around intelligent tutoring systems, and this work is more about guiding the student in their learning journey by giving them different kinds of problems to solve depending upon the mistake that they have made on a given problem. And we would also need these kinds of technologies even for the programming education. But programming is a very challenging subject in its own right, much more challenging than, let's say, initial math or other subjects that you might teach to students in middle school. Even if I give you one particular programming problem to solve, there is no unique solution to that problem. And this is what makes it grading or providing feedback extremely challenging. So some of the work that I described is focused more on that dimension, but the dimension that you're talking about is an orthogonal one and will also be important. That's why this is an effort that the community will all need to join hand and come together to solve. Many interesting different kinds of problems to solve, and some of them are along the dimension that you are pointing out.
Thank you.
Hi, good morning. So very interesting conversation on how AI is assisting programming tasks. But how about, like, let's say larger programs or applications development? Are there advances towards like AI? Let's say I want to build a mobile application, and then I'm like, hey, AI, build an application for me that does something, and then it generates an application for me. Are we there yet, or are we still far away from it?
So if I understand your question correctly, you're asking, are there advances in helping users maybe build new applications, like applications on the phone and so on?
Yeah.
So in fact, one of the product teams that we serve is called Power Apps, where the goal is to enable end users or low code, no code users to be able to easily build applications. And this team is probably one of the best that I have seen inside the company in terms of delivering AI-based advances to its users. So they recently came out with a capability for NL2 code based on some work that is also happening at in different parts of Microsoft research. We recently provided them 2 capabilities. One was programming by examples and being able to do repair of formulas. Multimodality is what you really need. So to build a specific application, sometimes you might want to map the data from some data source onto your application by doing some string transformations. This is where examples is a very good way to specify intent. Sometimes you just need to get started. So natural language might give you a skeleton to start with. Sometimes you might want to write the formula yourself, and this is where repair technology would be useful. So what I would say is that this product is already leveraging lots of AI advances in small different pockets. And in order to, the future forward is really about making it multimodal. So allowing the user to express all these different kinds of intent in a combined way, and also making it very interactive. So this is an aspect that I did not really got into, right? So you talked about doing a task which is much bigger, and this potentially cannot be specified right in just one go. But you can imagine the user saying something and then the system asking some clarifying questions or having an active learning based conversation in order to do that. But building these kinds of applications can be a very good test case for trying out this multimodality and interactivity.
Thank you.
Hey, Emerson Murphy-Hill, Google. So it's been really cool to see your research program blossom over the last decade or so, from Flashfill, like clearly brilliant thing, to being applied in all sorts of different areas. Do you have any sort of learnings about the process over that time, especially how to successfully grow an ongoing research program in bureaucracy?
So very interesting question. And so I would say that the process of going from a research paper to putting out a technology to real users is very involved. So for me personally, it took me, like if I take the example of Flashfill, it took me 3 weeks to develop a first implementation of Flashfill, and maybe a couple of more weeks to write a paper around it. And I could have been pretty much done. But I decided to spend 2 years engaging with the Excel team to get this technology out. And the beautiful part of that engagement was the new challenges that the product team pushes us onto, which has often led to new foundational advances. So for instance, when I was building Flashfill, the first implementation that I designed used to take 3 to 4 examples per task on average. And the Excel team insisted, oh, we cannot ship this unless you make it work with 1 example on most common cases. And I was like, but what's the big deal? What alternative does the user has? If they can provide 1 example, they can spend a few more seconds providing other examples as well. But they said that no, users are going to lose trust in your technology and they will never come back to it. And they were so right. I showed you this, this thing that went viral on Twitter where people made fun of Flashfill. And even today, when I read on health forums, people don't even realize that you can give more than 1 example. They complain that Flashfill is not working because the data is in 2 different formats, but you need to give 1 example for each of the two formats. So these kinds of observations that come from people who have a very different kind of background, engineers, program managers, user designers, I think is a blessing. That I feel privileged to be in touch with these people, to work very closely with these people, and to be able to use them for doing more foundational advances. So that's one. The other thing I'll say is that this is a constant process of iteration and refinement. And in case of building AI, this becomes even more so important. So one definition of AI that I sometimes use is that it is a technology or it is something that will not always work. Because if it always works, it's an algorithm. And when you are living in this world, you have a lot to gain by doing an iterative process where you build out something that is useful enough that people start using it. But then the interaction that happens with the users, the telemetry data that comes in, the customer feedback that comes in, can be very important, worth its weight in gold in order to train, more ML models, or to figure out what are the next set of problems you want to solve. So in that sense, I've been very grateful for the opportunity that Microsoft provides me through this interaction with these different product teams. So building AI iteratively, which I see is the only way. And secondly, that it has inspired many new foundational problem definitions for me, like synthesizing programs from zero examples or synthesizing programs from noisy traces, which is the basis behind IntelliCode suggestions.
Thank you. Let's take one last question and then we'll...
Thanks for the talk. I'm Khoi, an undergraduate from Fulbright University, Vietnam. So my impression is that the programming by example techniques works well for small DSL. So let's imagine I have a spreadsheet of numbers. So I think machine learning techniques can solve that problem, so the synthesis problem. But I cannot get out a interpretable formula from that. So how might we use programming by example to approach that problem?
Yes. So that's a very, very good point that you mentioned about, some of the next future directions in programming by examples is to how to scale these systems, which are designed to work very well for small niche domains. But what if you want to search for programs over a much larger domain? And one such thing that I did talk about in my talk was this Clashful++ system, which can now start handling some numerical transformations, some date time transformations, and so on. And the idea here was to combine the top-down, search with some notion of bottom-up analysis over the grammar. But you can even imagine, leveraging multimodality. So, for instance, for some numerical things, the intent might actually be better described using natural language. I might want to, compute average of two numbers or even multiply two numbers. And instead of really multiplying the two numbers and giving an example, you might even say things in keywords or natural language, and some combination of natural language and examples might also be very good. So scalability and multimodality are two, future directions of innovation to take, programming by examples much further.
Thank you.
Thank you very much. And now, as a last act, it's my pleasure to hand over a small memento from Singapore for Sumit to carry over back home for his keynote.
Thank you, Evan.
Okay, that will be all for the keynote and the opening session. Please enjoy the rest of the conference. Thank you.
Yes,